Hello, everyone. I'm Dr. Brian Courclay, and I'm here with Food Science Questions Answered. And I'm here to answer all of your questions posed by anyone through the comments, whether that's TikTok, YouTube, Instagram, or even just basic email. But let me know if you have a question and I'll answer it. And so let's get started. So, what I really like about this one is, this user really wants me to talk about EPG and modified plant oils. As you can see here, that there's a lot of question marks about that, mostly because EPG is called esterified proxylated glycerol. See, even I cannot necessarily pronounce these names. And what it is essentially glycerol that has been attached to, this propoxyl group. It looks kind of funny. It kind of resembles like a fat, so it has a lot of properties of fat. But the difference is that it's not digestible, so there's no enzyme that can break it down, and it basically goes through your body. And this was great because when EPG and another similar type of esterified fat replacer known as Olestra was invented, they thought, oh, this is going to solve all those issues about trying to replace fat because fat is really critical for a lot of flavor. It's used for creating crispiness. Fat is really important for a lot of different processes in food science and technology. But of course, something, there's always a cost. And so with EPG and Olestra, what ended up happening was that because people couldn't digest it, it would just go straight through people's body. And guess what? You'd have all these gastrointestinal issues. I'm not going to talk about them here, but you can imagine if you have a lot of oils that aren't being absorbed by your body and they're going straight through, all sorts of things are going to come out as well. Think about a lubricant, right? Think about some kind of motor oil that's just streaming through, and it's not a pleasant thought or experience. And so when food companies started including these in a lot of prototype food products, people were eating them by a handful, and reported getting some serious problems. And so they ended up having to roll back on the use rate. And it turns out that you can only really use 10 to 30% of the oils as this Olestra or EPG, because otherwise you end up with these problems. The rest still had to be high calorie oils and fats. So love that question. Love that whole issue. It's a pretty funny scenario that we all laugh about in the food industry. All right, here's our next question. So we have here, why do Fairlife protein shakes taste so good compared to other competitors? That's a really good question. And I would say that a lot of it has to do with the process in which Fairlife uses to what's called ultrafiltration. So in this case, they take milk and they run it through these osmotic pores, these micropores that remove some of the protein, it holds it back, and lets water and minerals and lactose through. And so you have a process that basically holds on to all the proteins and increases the protein content, but it also increases the content of a lot of other minerals and different components, and it concentrates it, right, in a fairly straightforward manner. But so, you get a lot of these components that increases Fairlife's, protein content, but also there's a lot of flavor in it. And on top of that, these protein shakes also they most likely include bitter blockers, which reduces any kind of off flavor or bitter flavor. They play around with the flavorings themselves. There's probably been a lot of development that was put uh, into these particular products, and you can imagine like, well, there's one thing to take, let's say like whey protein that's been produced from a cheese production process. It's a byproduct. It has to go through this whole process of being not only evaporated, concentrated, and then dried. There's a lot of different processes for drying it, but there's spray drying and drum drying, which both of them require a lot of heat, and that heat can damage a lot of the flavors. Now you have this powder, then you then have to redissolve back into water. Well, you've included all these, small components, of course, but they do create off flavors. And so that's going to contribute to your protein shake. That's going to add those off flavors in there. Whereas with the Fairlife process of doing the ultrafiltration, you don't have to go through that entire step. It's a non-heat treated step in which you're concentrating those proteins, and so you don't actually have to go through these scenarios where you could create a lot of off flavors. And I would say that's probably the main reason why Fairlife protein shakes taste better than other protein shakes because you're just going through a different process that doesn't require heat, and it's very, it's not going to be degrading on a lot of the components. So great question. I had this question I was asked on r Ask Culinary, which I really wanted to answer because it was about the science behind bovine Vietnamese meatballs. So I'm Vietnamese, and bovine is basically these funny little gelatinous meatballs that are kind of spam-like. Actually, not in terms of taste, but the texture. It's kind of quirky. And it's fairly commonly found in Vietnamese noodle soup dishes like pho. And the question really was like, why are we doing all these things to the Vietnamese meatballs when you make them at home? Like, why do you keep the meat ice cold? Why do you add baking powder to the meat? And then why do you add tapioca starch instead of, say, cornstarch? And so I went through this whole thing, and because being Vietnamese, I'm very excited to answer something like this. And so one, you cool down meat because what happens is that allows the muscle proteins to contract, and that gives you more of that chewy texture. And then once you boil it, it kind of locks that into place. Of course, as you're heating it up, it's gonna relax some of those muscle proteins, but ultimately, if you boil it fast enough, they're gonna denature, and so they get kind of stuck in sort of that, I would say, kind of like an accordion. So you're kind of compressing it with the cold temperatures, and then it's getting stuck in that position. With the baking powder is going to have two components. One is the baking soda itself. The baking soda increases the pH, and that allows for a lot of denaturation processes to occur a little faster. It also allows these cysteine bonds that exist in the muscle protein to get scrambled. So muscle protein is kind of a linear linkage of a lot of different beads. It looks kind of like a bead on a string where each of those beads is a protein, whether it's titin or it's actin or there's a lot of different proteins that are involved. But essentially, it is kind of a linear string, um, and those are all bound together internally by cysteine bonds. If you have a more basic condition, those cysteine bonds they break up, and then they start reacting to other cysteine bonds. So you have these linkages and then the neighboring linkages attach to each other and attach it and you get this whole kind of spaghetti entanglement that occurs, and so that's really the reason for that baking soda component. The other component is the phosphates. Now, phosphates are really good at binding calcium, and muscle tissue tends to have a lot of calcium because it's necessary for a lot of the action potentials. So when you're using up your muscles, you expend a lot of calcium. This happens to be how they work. Now, the phosphates can bind to that calcium and it gets stuck to it and it removes it from the muscle tissue. That allows the muscle tissue to be a little more gelatinous and it kind of breaks it down. And phosphates tend to be used a lot in sausage making. And that's how you get that breakdown of you have ground meat, which has, sort of the particles. Those particles kind of melt apart with the use of phosphates. So that's the other component. And then the last component, the tapioca starch. The tapioca starch has higher concentration of amylopectin, which is another starch, versus amylose. Amylose is starch in a very linear structure, whereas amylopectin is a lot more star-shaped, it's a little more branched. It's got a lot more chaos to it, so to speak. And so instead of dissolving like cornstarch tends to do, tapioca starch tastes more. It creates more of a thick coagulated paste. And that allows it to actually gel at a lower temperature than cornstarch. So what will happen is as you're boiling these meatballs, the denaturation process is going simultaneously with gelatinization process. And so that allows you to create the meatball in that sort of rubbery, chewy texture. So a lot of these components are really critical for the construction of bouillon. So I was very excited for this question. It was very nice to know something about my own people's cuisine. So very happy for that to be asked. Next question here. We've got a question from r Ask Science, which is why has bacteria not become resistant to cleaning or disinfectant sprays? And the reason why I'm answering this is because that's a really critical question for food safety. We use a lot of different disinfectants, whether that's bleach or hydrogen peroxide or peracetic acid. And ultimately, we're relying on the fact that microorganisms literally cannot chemically build a resistance to these compounds. Now, at really low concentrations or dilute solutions, they can. There's actually been research that has shown that microorganisms have developed a resistance to low concentrations of bleach, hydrogen peroxide, and even ultraviolet light. That being said, there's a limit. I mean, at some point, the chemistry is so harsh that you're just literally ripping apart molecules. You're breaking apart. So, it's one thing where an organism can survive the vents, the lava vents down in the deepest part of the ocean, uh, where the temperatures are near boiling point, and there are microorganisms that live there, and they live there fine. There's even vent worms that live there fine. They've evolved systems to sort of combat that. But the analogy is that the level of bleach or hydrogen peroxide or any other disinfectant that you use is kind of like lava. It's so hot that literally anything is going to melt. So if you end up evolving something that's so powerful that it can resist lava, you probably don't have many resources to combat anything else. So the idea here, the principle here is that maybe there is some organism that's able to resist disinfectants, but they're not likely to evolve the mechanisms to evade the immune system. So we're not really that concerned about microorganisms developing those types of resistances. And there's chemical reasons for that. At some point you just have to, while there are a lot of really specialized, very interesting microorganisms that survive in extreme conditions, they're known as extremophiles. None of these are pathogens, or at least none that I believe. They've worked so hard to adapt to those specific conditions. All right, back to the homepage of our food science. So let's get started here. Again, I'm not going to ask or answer questions uh, involving education and that sort of thing in career, unless I have a very specific opinion about it. So I'm going to skip over these. This person just submitted a little diagram from the chemistry of rum. So this is compound interest. I do like them. I really appreciate them showing a lot of the very fascinating chemistry in food. There's a lot of career questions here. I'm really surprised. So this one's interesting. So how is cocoa butter converted to powder form? You know, this is really interesting because you have cocoa powder, you have cocoa butter, and you have all sorts of different cocoa products, different chocolate products. So cocoa butter, of course, is an oil, but you can disperse it, or there's another process called alkalization, in which you convert it into a substance that's more ionic. So you add some kind of alkalizing agent, whether or not that's sodium carbonate or potassium carbonate or something along those lines, and that allows you to sort of separate a lot of the components of the cocoa butter, and then you can disperse it in some kind of carrier, whether or not the carrier itself is just the material of the cocoa itself, or if it's converted into something where maybe it's spray dried along with, I don't know, let's say tapioca starch or another powder, so it kind of is just bound together. That that's in principle. Specifically cocoa butter. I don't actually remember precisely how it's powdered, but that's the principal gist of it. I thought this was actually really funny here. So they have a fish in the refrigerator and it's bioluminescent. And so the only reason I find this really funny is because as a kid, I used to get fish from the pier because I live by the beach, and I actually asked my mom if she could ask the fishermen to give us their fish. And the reason why is because I used to really love these experiments with bioluminescent bacteria, and I was so curious about it because, I'd read these books in high school, and it would say, oh, you can take these bioluminescent microorganisms that grow on, the fish's skin, and then you can culture them in a petri dish. And of course, I was really lazy, and so I didn't end up buying a petri dish or pouring agar, but I did find a way to hack it, and I was able to scrape off, the skin of the fish, and I was able to make some kind of media where they were able to grow. And I did get bioluminescent bacteria, which was really exciting. It only lasted for a couple days because they don't survive above water or ocean water for very well. But it was really cool. I was really astonished, and that gave me a fondness for my love of microorganisms and microbiology. But yeah, I mean, it's not a big deal. That happens. And unfortunately, a lot of it they tend to be some kind of let me see if I remember the subspecies. So it could be there's like a fluorescens, Pseudomonas fluorescens, which is fluorescent, but there is also microorganisms that generate their own light. So it's a fascinating stuff. That's a whole different that's a whole different topic for sure. Here's another question. So, do probiotics survive heat from touching other warm food? Well, honestly, it really just depends on the temperature. So, if the temperature is above 45 degrees Celsius, certainly it's going to kill the probiotics, but a lot of them can survive anywhere between 25 degrees Celsius up to 42 or 45 degrees Celsius. They're not going to be super happy at the higher temperatures, but once they go down into your gut, they'll be fine. But anything above that's going to be a big issue for them. So it's not really recommended for you to mix probiotics with hot foods for that reason. It's not necessarily going to give you those benefits because they're pretty they're not super hardy, unfortunately. Those probiotics have a really hard time surviving in conditions that aren't optimized for them, which is why it's so difficult to make probiotics that are actually functional. So, yes. Another question. How to make drinks similar in texture to Frappuccinos with no ice? So the question here is, I'm addicted to Starbucks Frappuccinos. Stress coping mechanism. They study a lot. Okay, I get it. Caffeine. Got it. I like the thickness of the crunchy, mushy ice and slurpiness. Yeah, I mean, there's a lot of ways to do that. If you want that kind of texture, I would just go straight for gums, right? So you've got xanthan gum, you got guar gum, and together they have great synergy. You can use them at from 0.1% up to 0.5%, and they're going to give you some kind of like it's more of a gel effect. It's not necessarily going to be a slushy because ice broken up and starting to melt has a different texture and components. But you can certainly add sugar and creaming agents, fats, and that sort of thing. And that should kind of give you some approximation to that. You can whip it up, include sunflower lecithin. I would probably include some kind of protein like casein. That's really good at being whipped up, and you don't need that ice. So that would be my advice for that particular thing. Looking for suggestions for an alternative to psyllium husk for gluten-free baked and fried cracker. So this is really interesting because I've started investigating a little bit more about low sugar and zero calorie crackers and baked goods and that sort of thing because I've been working on different consulting projects on that. And ultimately, the biggest one that I've found that has the best properties for making these types of products is polydextrose. That seems to be the one that everyone uses pretty often. I would say it has better properties than other fibers. and other types of gums. You'll still have to use some just to sort of get that binding and gelling effect, but high dextrose definitely works really well as an alternative to starches. It's really remarkable the types of textures that you can get. And during the baking process, it has very similar chemistry and reactions. So I'd go for that for sure. Of course, I have great love for ice cream, and so this person's asking a question about what are you supposed to use in ice cream? Well, honestly, you have to use them all. I mean, it's the truth of the matter is that there's a lot of synergies that go along with producing ice cream, and really, what you're trying to do there's two main things that you want to do with an ice cream, which is A, you want to make sure those ice crystals are as small as possible, and B, you want to make sure that all the components are homogenized together. Right, so you've got protein, you've got fat, you've got water, you've got sugar, and all these don't necessarily mix very well together. And the magic of ice cream is that you create a homogeneous, or at least heterogeneous mixture that's so mixed together that you can't tell that's heterogeneous. Your phase particles are really small, so your domains are really small, and so you get that texture that just feels so creamy. And the idea there ultimately is you really want to reduce those ice crystal sizes because once the ice crystals get large, then all havoc breaks loose. The proteins stop dissolving, they create their own domains, the fats, they have nowhere to go because the proteins have nowhere to go, and the sugar just hangs out and it becomes a big mess. So, going back to the question, ultimately what you want in terms of gums is you want to use locust bean gum, you want to use guar gum, and you definitely want to use kappa carrageenan. So carrageenan comes in a lot of formats, and the one that's really the king of them all is kappa carrageenan for ice cream. And the reason why is because due to the structure, the ionic structure of that particular carrageenan, carrageenan is a polysaccharide or a fiber that contains sulfate groups. And so part of it is very charged. And so they align in such a way where they can sort of wrap around those ice crystals and form a barrier that keeps them from growing, which is a really fascinating process. You don't need a whole lot. That's what's remarkable. Your use rate's probably like 0.01%. You can even go lower, I think, depending on your composition. But you don't need a whole lot to really stop those ice crystals from forming. If anything, that's the only thing that really needs kappa carrageenan. But the rest definitely are beneficial for their synergistic effects that cover a lot of the weaknesses of carrageenan. Um, it's fun stuff. I think ice cream is a really fascinating topic, and there's so much to explore with that. I'm going to take a quick break here. Definitely have a consulting call, so I need to get that done, but I'm going to jump right back in.
2,000 years later.
I'm just gonna jump back in after doing my consulting call. Very interesting stuff. Very, very interesting project. So here we have our next question. Cannabis beverage production. This person's looking for insight about THC in beverage production, and I have to admit, it is very difficult to do. There's a lot of restrictions right now, and of course, there's some really interesting gray areas in the cannabis beverage space. Um, Honestly, the biggest takeaway nowadays is that there's a loophole in a lot of number of states in which you can use an extract of hemp, which is made up of 0.3% THC and other cannabinoids. And by using that loophole, you can include hemp extract in a beverage, and then you can have a psychoactive beverage without necessarily saying it has cannabis. So yeah, it's a very interesting space. There's a lot of new developments. I'm sure that a number of states are closing that loophole, but very fascinating stuff in terms of regulation. Um, Honestly, I don't actually know that much because it's so unknown. I mean, I've been working with different you know, clients and different companies, and some of them are having trouble doing testing because they can't ship their product out of state, which is super wild if you think about it. Just because of this, some states can. have cannabis be legal, some cannot, and then it's federally illegal. It's really weird. So I have companies that, they don't even do testing on their products because they can't. Even the ones within the state won't do it because it has cannabis. It's a really, really super gray area. Authority letter, I don't even know how you could get one, considering that you can't even demonstrate that your product is shelf stable. Um, Weird stuff. Anyway, and then here we have creating a shelf stable dairy beverage. So this person has been brewing dairy-based tea. I imagine it's something like a chai tea. And then the question is like, how long do I pasteurize a product? If it's hot filled and immediately chilled, and are the ingredients I can experiment with that would result in non-refrigerated version? This one's really hard. And the reason why is because dairy can be challenging to pasteurize. If you muck it up and if your temperatures are too high, you're going to burn it or you're going to create a lot of off flavors. If your temperature is too low, it takes too long to pasteurize. Now, that being said, obviously not everyone has a pasteurization system. That's a very complicated design. I used to work in a dairy plant, and they had to clean it like once a month, the pasteurization, because it's so thin and it's so small. It's like two plates that get heated, and then the milk goes upward in these little tiny chambers. And over time, the protein breaks down, and you get this muck that grows inside the pasteurizer, and you got to clean it with caustic solutions. It's really a mess. So ultimately, what you want to do, I think, for someone that's producing something at the low level, if you want to create something that's shelf stable, that is to say, it still has to be refrigerated. It's really hard to do a non-refrigerated version without having ultra pasteurization, which is like an extreme version of pasteurization where you take the temperatures really high and you need a lot of pressure. Is what you would like to use is a long-term low temperature pasteurization process. So what you can do is if you hold the product, so you raise the temperature to 163 or 165 degrees Fahrenheit, and you have to hold it for a minimum of 35 minutes, and then you cool it down. And mind you, it should be in the beverage container. Um, Usually, people do not have the capability to do aseptic transfer from a vat. That would be really complex. But yeah, you would do it in a container, and then again, you still have to validate it with microbiology tests to ensure that it's actually safe. But you cool it down, and that should buy you at least 14 days. Yeah, dairy is whack. Dairy is very difficult. Don't recommend it as if you decide to do some kind of dairy product, it's don't do it as your first product. It's creating a snappy ice cream dip. So this person is trying to develop an ice cream bar. Dip recipes online use a combination of coconut oil and chocolate. It dips well, but freezes softer than I'd like. The more chocolate I add, the snappier it gets, but it dips worse, falls off the bar. Is there a more complex method to make dip? Well, ultimately, you're really what you want is something that melts well, but then has very strong crystalline structure when it's frozen, right? And so, of course, the more chocolate you have, more crystal structures that you can build versus something like coconut oil or any kind of oil or fat is going to sort of create more of a creamy texture, right? Yeah, and so ultimately what you need here is you need emulsifiers, and you need compounds that are going to reduce the melting point of the chocolate. Because if you have a very high chocolate concentration, it's going to be a lot harder to melt. Usually I'd probably include something like sunflower lecithin, some other kinds of emulsifiers, um, possibly just add cocoa butter, right? So cocoa butter has very similar structure. I mean, it has the same fat structure as the chocolate itself, and the cocoa butter is gonna be able to create more of a hard snack, compared to something like coconut oil, or any other kind of oil because those are very similar crystal structures, and they're going to create good alignment and good crispiness. All right. How to calculate the carb content of bread dough based on how long it was fermented. If I weigh the yeast, flour, and measure the temp and humidity, can I approximately estimate the amount of carbs the dough will have? No. I mean, like to a horrible approximation. Yeah, that's wildly inaccurate. That's gonna be really difficult to do. There's a lot of aspects and conditions that will affect how fast the yeast will break things down. For example, yeast will consume only sugars and will only metabolize sugars. So there's going to be some residual starches like amylases in the flour that breaks it down and converts it into sugar. So it all really depends on how much amylase there is in the flour, and that will determine the speed at which the yeast grow, as well as the initial sugar content in the flour and any other residual microorganisms that may be breaking down the flour starch and converting it to sugar. And then that's just one aspect. You've got your amino acids, you got your minerals, you got the water content, the pH. There are so many variables associated. So, yeah, I mean, I'm sure someone has done it, but in a very, very defined setting and a very defined set of parameters in order to determine or estimate the amount of carbohydrates that are left over. It's going to be a lot. I mean, yeast aren't particularly well suited to breaking down the starches in flour. It really is all about those leftover amylases that break down the flour into sugars. They do have a little bit of ability to metabolize starches, but it's very limited. This was interesting. Any idea how I can recreate the flavors from Monster energy drinks? Uh, the big thing here is that a lot of money goes into developing those Monster energy drinks and those flavors. It takes a lot of money and a lot of time to develop those flavors. So, highly do not recommend trying to uh, I guess, back engineer or reverse engineer these flavors. It is very complicated. And even if you manage to do some kind of like gas chromatography, mass spectrometry, where you're able to analyze the compounds that are in the flavor, you're not really going to know what to do with them because you don't even know the concentrations. So, yeah, you'll end up with 20 different compounds and not really know which one's which and why they're important in the composition of the Monster Energy drink. Don't recommend it. Super complicated. It's complicated, not worth it. Help with starch and enzyme syrups. So this person wants to make some syrups using enzymes. This one's always really interesting. And so one of the issues is that one of the syrups only ends up mildly sweet, the yield is very low, and has a bit too much acidity. So yeah, converting starches into enzymes is a complicated business. There's a lot of different enzymes that are actually involved. We call them all amylases, but there's alpha amylase, beta amylase. There's there's different there's maltases, there's all sorts of enzymes that break down the starches into different components. So one of those enzymes chops up the chains that are on the outside of the starch. So if you imagine starches being composed of two different components, one being amylose, which is linear chains of glucose attached to each other, the other being amylopectin, which are branch versions of glucose attached to each other. If you can imagine, it's kind of like a snowflake. Those have two different properties. So the linear chain one, you can slice it into the little parts. But the ones that are branched out, the enzyme can't really come in there and get in there and break it apart. So you actually have to break it from the ends and fragment the ends. So you have two different starch fractions that have completely different properties. And on top of that, some of those starches are actually crystallized, which makes it even more difficult for those enzymes to get in. So you do have to do some initial processing, gelatinization, heat treating, boiling, um, to sort of break up the initial structure of the starches. But once you do, now comes the question. Once you have the chains broken up, what do they form? Well, they form smaller chains, and then the smaller chains have to be broken up into smaller pieces in order to end up with sugars. So, you know, there's a lot of mucking around. Like, for example, if you're trying to make oat milk from oats, You can just throw in the amylases, but there's a lot of work to be done in terms of so many different parameters, what temperatures to use, how to stop the process, because you don't want it to go all the way. I mean, you could have a syrup that's completely just sugars, but if you did that, then you don't necessarily have the body. So there's all sorts of things. You don't want the temperature to be too hot, because then that will deactivate the enzymes. You also don't want the enzymes to be too cold because A, they won't work as fast, but then B, you might also have microorganisms growing. And that's part of why there's sort of this acidity that this person's pointing out, which is that there are certain microorganisms that can survive at fairly high temperatures, or at least on the edges of the fermentation, around 50 degrees Celsius, surprisingly, and they produce a lot of acid. So complicated stuff. Yeah, there's a lot involved. There's a lot of math involved, surprisingly. Oh my gosh, Boar's Head plants nationwide now part of law enforcement investigation, USDA says. This has been really hard for me to see because honestly, the food industry should not be in a position where people are dying. That's a horrible, horrible scenario. And honestly, there's a lot of negligence that's involved. I will be really surprised to see what will come out of this particular investigation and what the lawsuits that will be involved with this is because people's lives have been damage or lost in this scenario. And that really puts us in a defensive position as a food industry because I think a lot of us are trying to do what's best in terms of food safety. That it doesn't necessarily always mean the most healthy, but it does mean that the food is stable and ensures that you don't see scenarios like this. But it is what it is, and so it just makes me think how much involvement you can have and what are the important parts in terms of this work conveying the right information. I if if there was a continued engagement, I wonder how much I might have been involved in this, and what could have been implemented. So it's a little scary, right? Like as a food science consultant, there is that aspect of having people trust you to deliver the right kind of knowledge and information. Let's see here. Skipping along here. I'd like to create a hot sauce and bottle it for the first time. With plans to go commercial in very small batches, what process do I go for? There's seemingly so many. Well, definitely make sure that your pH is low enough. Ideally 3.3. 3.3 is awesome. Even lower than that, superb. You're really not going to grow anything. Anywhere between a pH of 3.3 and 4 is like okay, but you're going to get some spoilage. And then above 4.1 to 4.6, kind of scary, especially if your pasteurization or heat treatment process is not aligned well, and you're not getting the right temperatures, or you ended up not adding enough salt. There's a lot of parameters that can impact the food safety of something like that. But ultimately, yeah, you want to make sure that your pH is low. You want to make sure, if you can, have some salt to ensure that there's really low risk of any microorganisms growing. And making sure you have the right time and temperature for pasteurization. There's actually a really great document that was produced by University of Wisconsin that shows sort of the temperatures that are required for acidic goods at different pHs. So let's see, temperature, pasteurization, canning. Let's see if I can find it. Yeah, this is a good one. So I love this one. I always refer to it. Um, of course, University of Wisconsin Mass is my alma mater or my Ph.D. And so they have really great information about, you know, what you can do in terms of pasteurization and heat treatment as well as hot filling. I juice citrus. Why is it bitter? So this person was juicing different oranges and mandarins and so on and so forth. Well, there are compounds found in the seed and in the pith, if it does end up making it into the beverage, that are quite bitter. They might not necessarily be bitter in the beginning, but as it continues to dissolve, because they are fat soluble, it takes some time for them to be dispersed into the solution. And this person said that it ended up very bitter after leaving it out for 12 to 24 hours. And that's usually why, is because those components, it takes some time for them to get in. Um, and eventually once they do, they're really hard to remove. Yeah, I think that's it. I think we're good. I mean, there's always questions, of course, and if you have any, please send them along. I'd love to hear them. Put them in the comments, whether or not you're on TikTok, on YouTube, on Reddit, or shoot me an email. I'd love to hear from you. But this is Dr. Brian Quokley, and thanks for checking us out. Talk to you soon. Bye.